You ever see a firework display and wonder, how do they get all those amazing colors? Or why is a sodium street lamp that specific kind of intense yellow? Well, the answer to all of that is hiding inside the atom. And in this explainer, we're going to unlock the secrets connecting atoms to light and color.
So let's start with the big question right up front. Why do different elements give off different colors? I mean, a firework with strontium in it burns this deep crimson red, but one with copper burns green. It's not random. There's a reason for it. And the secret, believe it or not, is hidden deep inside the structure of the atom itself. To even begin to answer that question, we first need to look at the most famous spectrum of them all, a simple rainbow. It actually holds the first major clue.
Right, so we've all seen a rainbow. You know how the colors just spread out in this perfect, continuous band? There are no gaps. Red just smoothly fades into orange, which fades into yellow, and so on. The key word here is continuous. We call this a continuous spectrum.
Now, this specific band of colors that our eyes can actually pick up is called the visible spectrum. But, and this is super important, this beautiful rainbow is just a tiny, tiny slice of all the light that's out there. I'm talking radio waves, microwaves, X-rays. Our eyes are only tuned into this very narrow window.
So what makes red different from violet? It all comes down to its wavelength. Think of light as, well, waves. Red light has these long, lazy, stretched-out waves. Violet light, on the other hand, has much shorter, choppier waves that are all bunched together. So longer wavelength for red, shorter wavelength for violet.
Okay, so we're saying light acts like a wave. But what does that actually mean? Like, what is a light wave, really? Let's dig into the physics a little bit.
So, you know how if you drop a rock in a pond, it makes ripples? It's kind of like that. When an electric charge, like an electron, vibrates or wiggles, it creates a ripple. But this ripple is an electromagnetic wave. It's made of a vibrating electric field and a vibrating magnetic field, and they're perfectly at right angles to each other. And guess what? Visible light is exactly this kind of wave.
All right, get ready, because here comes an equation you absolutely have to know for your exams. It's C equals V lambda. C is the speed of light, and that's a constant. It never changes. Nu is the frequency, which is just how many waves pass a point every second. And lambda is the wavelength we just talked about. Because C is always the same, this means frequency and wavelength are inversely related. If the wavelength gets shorter, the frequency has to go up to compensate. They're locked in this dance.
Now let's take this idea of waves and connect it to something we can all feel: heat, or more specifically, energy.
So remember that bigger picture I mentioned? Here it is. This is the whole electromagnetic spectrum. Look at all this stuff. You've got super high energy gamma rays way over on one side and super low energy radio waves on the other. And our visible light, it's just that tiny little rainbow slice right in the middle. And you can actually see the link between energy and light with your own eyes. Just picture a blacksmith heating up a piece of iron. As it gets hotter, it starts to glow. First a dull red. That's lower energy light. But as you crank up the heat, pumping in more and more energy, the color changes. It goes from red to orange to yellow. And if you get it hot enough, it'll even glow bluish white. More heat means more energy, which means a shorter wavelength of light.
This very clear link between the energy you put in and the color of light that comes out, well, it led to a totally revolutionary idea that flipped physics on its head.
A scientist named Max Planck came along and said, hey, what if energy isn't continuous? Think about a ramp. You can stand at any height you want on a ramp, right? But what about a staircase? You can be on step 1 or step 2, but you can't hover in between the steps. Planck suggested energy is like the staircase. It's quantized. It can only be gained or lost in these specific, discrete packets, which he called quanta.
And he put that entire incredible idea into this beautifully simple equation, E equals h nu. This is another one you gotta know. It says the energy, E, of one of those little packets of light, one quantum, is equal to its frequency, nu, times a tiny number called Planck's constant h. So really simply, higher frequency light means higher energy packets.
And boom! This explains everything. We can now see exactly why blue light is high energy and red light is low energy. A single packet, or quantum, of blue light just carries a bigger energy punch than a quantum of red light, all because its frequency is higher. It's that simple. Okay, we've collected all the clues now. We've got wavelength, frequency, and this idea of quantized energy. Let's put all the pieces together and finally solve the mystery of why different elements have their own unique colors. So what happens when we do those experiments in a lab, when we heat up different chemical compounds? It's pretty amazing. They don't just glow white or make a rainbow. No, they emit very specific colors. Copper gives you that vivid green. Strontium gives you a brilliant red. And sodium, well, that's the intense yellow you see in so many streetlights.
And here's where it gets really cool. If you take that light, say the green light from the copper, and you pass it through a prism, you don't see a mini rainbow. Not at all. What you see is a series of sharp, individual lines of color. We call this a line spectrum. It's not a continuous band of colors, it's just a few very specific wavelengths that element is allowed to give off.
And that, right there, is the answer to our entire mystery. That line spectrum is a unique atomic fingerprint. Seriously, no two elements have the same pattern of lines. Just like your fingerprint is unique to you, the light an atom emits when it's energized is unique to that element. This is how scientists can look at a star millions of light years away and tell you exactly what it's made of.
Okay, wow, we covered a ton of ground there. So let's do a quick-fire recap of the most important things you need to lock in for your exams.
Okay, number 1. Light is a wave, and its wavelength and frequency are always tied together by C equals nu lambda. Number 2, the energy of that light isn't continuous. It comes in packets or quanta, and you can calculate it with Planck's equation, E equals h nu. Number 3, when you heat up atoms, they don't make a rainbow, they only emit light at very specific wavelengths. And finally, number 4, that unique pattern of light is called a line spectrum, and it's basically the element's atomic fingerprint.
So, the next time you look up at the night sky and see a firework explode in a shower of brilliant green or a deep, powerful red, you'll know exactly what you're seeing. It's not just pretty colors. You're actually seeing the unique light signatures of the elements inside, their atomic fingerprints being painted right across the sky.